All right, so like I said, we're going to continue with Laplace transforms. On Monday, we went through a whole bunch of different properties of the Laplace transform, and then we ended with a big table. Today, we're going to actually start applying it to solve problems, and then we'll be using it throughout the rest of the course repeatedly. So when we say the inverse Laplace transform, what we're really meaning is that we're trying to find some time function from a corresponding Laplace transform. And there are several methods for finding this inverse Laplace transform. We're going to consider two here. The first is just to use tables to find the time function itself. And the second technique is to use what is known as the partial fraction expansion method, which is what we're going to cover today. So if we're given some Laplace transform f of s, our goal is to break it up into components such that finding the inverse Laplace transform of those components is easier than finding the inverse Laplace transform of the original f of s. So for now, we'll assume that we have broken up our Laplace transform, and so we'll have f of s equal to some linear combination of components, so f1s plus f2 of s plus plus up to some fn of s, or some finite finite value of n. And then if the inverse Laplace transform of those components is readily available, then we can find the Laplace or inverse Laplace transform of our original function f of s as being the inverse Laplace transform of each of those components. So our entire goal will ultimately be to break up the original Laplace transform into components that are just easier to take an inverse of, such that you don't need tables to identify them. And then this will then allow us to find the time response. So in this case, this f of t is going to then be equal to the linear combination of f1 of t plus f2 of t plus up to fn of t. So in problems in system analysis or system dynamics, we'll often have some Laplace transform of the form f of s is equal to a polynomial b of s divided by another polynomial a of s, where generally the polynomial b of s has a lower degree than that of a of s. All right, so the advantage of this partial fraction expansion, I left out the fraction here. I'll write that in green. So the advantage of this partial fraction expansion method is that these individual components of f of s will end up being very simple functions of s, which then means that it's going to be relatively simple for us to take the inverse Laplace transform. We'll end up seeing the same inverse Laplace transforms many, many times over. And then as a result of that, we won't need to refer to tables. They won't need to memorize long tables. You'll just need to memorize a few Laplace transform pairs, particularly exponential terms, and then sines and cosines are the most common ones we'll see. Okay. So in order to do this, we must know the roots of a of s, and we must factor it as well. And we'll deal with that soon. So first, we're going to consider f of s in the factored form that I'm going to write here. We're going to say that f of s here is equal to, again, it's a polynomial b of s divided by a polynomial a of s. And we'll expand this into a fraction, some constant k, times s plus z1, that's our first zero, times s plus z2, that's our second zero, plus times s plus z sub m, and that is the mth zero. We don't necessarily need to factor the numerator, but it is beneficial if you do. It just makes it a little bit easier. You do need to factor the denominator, where we'll have our poles. So here we'll s plus p1, that's our first pole, multiplied by s plus p2, our second pole, all the way up to s plus pn, where that is the nth pole of the system. And here we have n is greater than m. And we'll deal with what to do when m is greater than n, or when they're equal to each other. Okay. So yeah, if the order of b of s is greater than that of a of s, then we actually have to do the division, which will produce some polynomial plus a remainder, and then we'll expand the remainder using this partial fraction expansion technique. And I just checked, we won't actually do an example where we need to do that, because it's not very common that arises in dynamical systems. Okay, we're going to start by looking at the case where we'll do this partial fraction expansion when f of s only has distinct poles, so that means there are no repeated roots in the denominator. And in this case, we can always expand f of s into a sum of simple partial fractions. And so in this case, we can write that f of s equal to b of s divided by a of s is equal to some constant a1 over s plus p1 plus constant a2 over s plus p2 plus plus an over s plus pn. So we can always expand into this sum of partial or simple partial fractions. And in this case, these will each have a very simple inverse Laplace transform. So the coefficient, or each coefficient ai here from I equals 1 up to n is called the residue at the pole s equals p sub I. So that would be the ith residue at the ith pole. We're going to find the value of each of these residues by multiplying both sides of our equation 68 by s plus the ith pole, and then letting s equal minus p, and then this will give the following. And you'll see how this actually works when we go through the examples. So we're going to first multiply s plus pi times b of s divided by a of s. That evaluated at s equals minus pi. This is then equal to our partial fractions with a1 over s plus p1 times s plus pi plus dot 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 plus ai over s plus pi times s plus pi plus dot 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 plus an over s plus pn. That's s plus p times s plus pi. This will all be evaluated at s equals minus pi. So on the right-hand side, we are going to end up eliminating every single term except for a sub I, because every single term is going to be multiplied by 0 because we have s plus pi, and s is going to be equal to minus pi, so that will give us 0. And as a result, we'll eliminate every single term on the right-hand side except for a I, and then this will give us that a sub I is equal to everything that was on our left-hand side before, s plus pi, that quantity multiplied by b over s times a, or divided by a of s, all of that evaluated at s equals minus pi. So if P1 and P2 are complex conjugates, then A1 and A2 are also going to be complex conjugates. And what that means is that you only need to find one of those, A1 or A2, because the other one's automatically going to be known because it's the complex conjugate. So the benefit of this partial fraction decomposition is that when we go to take the inverse Laplace transform of AI divided by S plus PI, this is equal to a sub I times e to the minus p sub I t, such that our function f of t becomes equal to, again, the inverse Laplace transform of its Laplace transform, which is then equal to some a1 e to the minus p1 t plus dot 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 plus ai e to the minus pi t plus dot 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 and plus an e to the minus pn of t. And so as a result, whenever we do this partial fraction decomposition, whenever we take the Laplace transform, it's provided that we have the form shown up here, we will always end up with a linear combination of exponential terms. Now we're going to go through two examples. I'll solve the first one, and then I'll have you guys work on the second one before I solve it, and then we'll go on from there. So we're given a Laplace transform f of s is equal to the quantity s plus 3 divided by s plus 1 multiplied by s plus 2. We're asked to find the inverse Laplace transform of this. And we're going to use partial fraction decomposition method in order to solve this. In order to do that, we're going to write out our f of s is equal to the fraction s plus 3 divided by s plus 1 times s plus 2. This will be equal to sum a1 divided by s plus 1 plus an a2 divided by s plus 2. From here, we're going to go and solve for a1 and then for a2. For a1, this is going to be equal to, we're going to multiply fraction form of f of s by s plus 1. So we'll get here s plus 1 times s plus 3 divided by s plus 1 times s plus 2. This will be evaluated at s equals minus 1. The s plus 1's cancel in the numerator and the denominator, and so we will get here s plus 3 divided by s plus 2, evaluated at s equals minus 1, which we can substitute in. We'll get minus 1 plus 3, and then minus 1 plus 2, and then this will be equal to 2, such that our a1 is equal to 2.
Why do we know to put s at -1?
So -1 is the first pole of this system. And so we're looking for what makes each of these terms here 0. And so if s is equal to minus 1, you'll get a 0 in the denominator. If s is equal to minus 2, you also get a 0 in the denominator. So those are the poles of our system. And so that's what the next one, to find a2, we're going to set s equal to minus 2. Yeah.
So we're looking for the discontinuities, pretty much?
We're looking for the... I mean, it is a discontinuity-ish. The correct way to say it is we're looking for the poles. That's what we're looking for.
That's like, it's similar, just like the pole is that.
Yeah. I mean, a discontinuity, it's not really a discontinuity. A pole is not necessarily a discontinuity. Discontinuity implies that there's a jump from one value to another value suddenly, instantaneously at a particular value of the input.
I guess more on the, where it's undefined.
Yeah, it is undefined. I mean, it's infinite response. That's what happens at the poles.
Okay, that's just what I like to make sure.
Yeah, so it's not discontinuity. It is it's infinite. You get things that blow up to infinity, just like when you force a resonance. Natural frequencies are poles. Okay, for A2, we're going to do the same thing, except we're going to use the second one, s plus 2. So we multiply s plus 2 times our original fraction, s plus 3 divided by s plus 1 times s plus 2. This will be evaluated at s equals minus 2. That is the pole for this. And then we get to eliminate our s plus 2, and we'll end up with here s plus 3 divided by s plus 1, evaluated here at s equals minus 2, which will be equal to minus 2 plus 3 divided by minus 2 plus 1. And this will end up equaling to, we get 1 over minus 1, so this is minus 1. And therefore, A2 equals minus 1. And we now have completed our partial fraction decomposition. At least we know what the residues are. And we can write this out as 2 divided by s plus 1 minus 1 over s plus 2. From here, we're going to take the inverse Laplace transform of f of s, and then this will give us our time function f of t. This is equivalent to taking the inverse Laplace transform of 2 over s plus 1 minus the inverse Laplace transform of 1 over s plus 2. And this is then equal to 2 times e to the minus t minus e to the minus 2t, such that the time function f of t is equal to 2e minus t minus e to the minus 2t. And this is true for t greater than or equal to 0.
Why is it only c is greater than equal to 0?
Because the Laplace transform is only defined from 0 to infinity. So everything we've been looking at is only valid for t greater than or equal to 0. And also, all of the functions we defined, we said were 0 for t less than 0 as well throughout the notes. Completed or got the right answer, so I'm just going to go ahead and solve this here. So we have f of s is equal to the fraction s plus 2 divided by s plus 1 times s minus 3 times s plus 5. This is then equal to, we're going to decompose this into 3 partial fractions, a1 divided by s plus 1 plus a2 divided by s minus 3 plus a3 divided by s plus 5. For a1, we will get that this is equal to s plus 2 divided by s minus 3 times s plus 5, evaluated at s equals minus 1. And we'll find that this is equal to, well, minus 1 plus 2 divided by minus 1 minus 3 times minus 1 plus 5. And we'll find that this is equal to minus 1 over 16. For A2, we'll do the same thing. In this case, we will get, hold on a second. Yep, yeah, we'll get s plus 2 divided by s plus 1 times s plus 5. That evaluated at s equals 3. This will give us 3 plus 2 divided by 3 plus 1 times 3 plus 5. And then if you evaluate this out, it's equal to 5 over 32. For A3 then, we'll get s plus 2 divided by s plus 1 times s minus 3. This is evaluated s equals minus 5. This is then equal to minus 5 plus 2 divided by minus 5 plus 1 times minus 5 plus 3. And this evaluates out to be minus 3 over 32, such that we can write that f of s is equal to minus 1 over 16 times 1 divided by s plus 1 plus 5 over 32 times 1 over s minus 3 minus 3 over 32 times 1 over s plus 5. Then the inverse Laplace transform of f of s will then be equal to minus 1 over 16 e to the minus t plus 5 over 32 e to the 3t plus, so actually minus 3 over 32 e to the minus 5t. Such that f of t is equal to minus 1 over 16 e to the minus t plus 5 over 32 e to the 3t minus 3 over 32 e to the minus 5t. All right, we're going to consider now a function f of s that has a quadratic factor, some s squared plus as plus b in the denominator. If this quadratic has a pair of complex conjugate roots, then it's going to be easier to not factor them, because then you get to avoid using complex numbers. So for example, we're going to consider here, I'll move this down. We're going to consider here f of s equal to, just as an example, some p of s divided by s times s squared plus as plus b. Where here a is greater than or equal to 0 and b is greater than 0. So if this polynomial s squared plus as plus b has a pair of complex roots, then we're, instead of going to expand f of s into, in this form here, we'll have f of s equal to some c divided by s, because we have our first pole right here, as s equals 0, plus some d times s plus e divided by our polynomial s squared plus as plus b. Our goal then is to express that second term into the following form, where we'll have ds plus e divided by s squared plus as plus b We want to express this into two fractions. Some constant big X1 times S plus alpha divided by the quantity S plus alpha, that quantity squared, plus an omega squared, plus another partial fraction, big X2 times omega divided by S plus alpha, this quantity squared, plus omega squared. We're here, alpha, omega, big X1 and big X2 are all constants. All right, and so in this case, then the Laplace transforms become inverse Laplace transform of our first fraction, big X1 times S plus alpha divided by S plus alpha quantity squared plus omega squared plus the inverse Laplace transform of big X2 omega divided by S plus alpha quantity squared plus omega squared. And these are equal to some big X1 times e to the minus alpha t times the cosine of omega t plus x2 times e to the minus alpha t times the sine of omega t. Okay, we're going to take a look at example 3 here. We're given the Laplace transform 2s plus 12 divided by s squared plus 2s plus 5. We're asked to take the inverse Laplace transform of this guy. You can factor this denominator, s squared plus 2s plus 5. You can factor this as s plus 1 plus 2j. So that's our first complex root, and then s plus 1 minus 2j. That's our complex conjugate pole. As a result, because we get complex numbers here, we're going to avoid factoring that quadratic expression, and instead we're going to recognize, or at least attempt to do this. We're going to recognize that here that we can rewrite s squared plus 2s plus 5. We can rewrite this as s plus 1, that quantity squared, plus, we'll write here 2 squared. Such that in this case we have alpha equal to 1, omega equal to 2. So from here, our goal is to expand f of s, which is equal to 2s plus 12 divided by that s squared plus 2s plus 5. Our goal is to then expand this into some fraction where we have this, well, we can just rewrite s plus 1 as quantity squared plus, we'll just leave it as 2 squared. From here, we are going to split up the 2s plus 12. We're going to want to put it into a form where we have a constant and then something plus a constant times s plus alpha. And so in this case, we can write this as 10 plus 2 times s plus 1, such that we can then split this up further. We can write this as 5 times 2, that's 5 times r omega, s plus 1, that quantity squared, plus 2 squared, plus fraction 2 times s plus 1, divided by s plus 1, that quantity squared, plus 2 squared. At this point, we're now ready to go and take the inverse Laplace transforms of each of these terms. So inverse Laplace transform of f of s is going to be equal to, this first term is going to give us the damped sinusoid term. So we'll get 5 times e to the minus 1, or e to the minus t, times the sine of 2t, plus, and the second term gives us the damped cosine. We'll get 2 times e to the minus t times the cosine of 2t, such that our time function f of t is equal to 5e to the minus t times sine 2t plus 2e to the minus t cosine of 2t.
How'd you get x2, 2 times s plus 1?
Sure. You're talking about from like here, right?
Yes.
Yeah. So you're basically just looking for some combination. So we have s plus 1 in the denominator down here. And so we're trying to build that up into the numerator as well. So we want to break up our numerator in a way that allows us to have eventually we'll have something times this omega term, and then we'll have something times s plus this alpha term.
I got it.
Yeah. Okay, we're going to look at now what to do when you have repeated roots. We're going to do this through an example because it's just a mess if you do it generically. So we're given the following Laplace transform, and in the denominator we have this s plus 1 term cubed, so we have a repeated root in that case, or a repeated pole. We want to express this fraction into, this fraction to partial fraction, so f of s will be equal to, just in general, b of s divided by a of s, which is then equal to, in this case, we're going to express it as b3 divided by s plus 1, that quantity cubed, plus b2 divided by s plus 1, that quantity squared, not cubed, plus b1 divided by s plus 1. So at this point, we're going to multiply both sides by s plus 1 cubed. So we'll get s plus 1, that cubed, times b s over a of s equal to b3 divided by s plus 1 cubed plus, oops, let me rewrite that. We're going to end up with b3 plus b2 times s plus 1 plus b1 times s plus 1 squared. At this point, we're going to then set s equal to minus 1. And on the right-hand side, we'll just get b3. So we'll just say set s equal minus 1. And then we'll get b3 is equal to this quantity s plus 1 cubed times b of s divided by a of s. This evaluated s equals minus 1. And for our examples shown here, and also we're going to call this equation up here E1. That equation over there, not the set sentence, but the equation before it. Carrying this out, we're going to get here, looking at our Laplace transform at the very top here, we're going to eliminate the s plus 1 cubed in the denominator. And so we'll just get s squared plus 2s plus 3, evaluated s equals minus 1. And this will give us 1 minus 2 plus 3 equal to 2, such that b3 is equal to 2. So then to find b2, we're going to differentiate that equation E1. So we're going to differentiate this equation E1. This is going to give us d over ds applied to s plus 1, this quantity cubed, times b of s divided by a of s. Is then equal to b2 plus 2b1 times s plus 1. From here, we're going to plug in s equals minus 1. And this gives that b2 is going to be equal to d over ds applied to this s plus 1 quantity cubed, b of s over a of s. All of that evaluated s equals minus 1. This is then equal to d over ds applied to s squared plus 2s plus 3 evaluated at s equals -1. We'll find that B2 is then equal to first 2s plus 2, evaluated at s equals -1. And then this is equal to -2 plus 2 equal to 0, such that B2 is equal to 0. I'm going to call this equation up here E2. All right, to find then B1, we are going to differentiate E2. So differentiating E2 gives the following, that d squared over ds squared times the quantity s plus 1 cubed times b of s divided by a of s is going to be equal to 2b1, such that b1 is equal to 1/2 d squared over ds squared times s plus 1 quantity cubed b of s divided by a of s so b1 is going to be equal to 1/2 d squared s squared applied to this s squared plus 2s plus 3, and now evaluated at s equals -1. This ends up being 1/2 times 2 equal to 1, such that b1 is equal to 1. Okay, so then thus our f of s is then equal to 2 divided by the quantity s plus 1 cubed plus 1/s plus 1 then we can go and compute the inverse Laplace transforms, and we'll find that f of t is equal to the quantity t squared plus 1 times e to the minus t, true for t greater than or equal to 0. Okay, your classwork assignment for today is going to be to turn in your completed solution to this example 4. Okay. We're going to move on to how to solve linear time invariant ODEs, which is what we've been studying up till now. The nice thing about this Laplace transform method is it yields the complete solution of a LTI ODE, and it automatically takes into account the initial conditions. So the method involves 2 steps. The first is to convert the ODE into some algebraic expression or equation in S, and then our goal is to then obtain the Laplace transform from the dependent variable by rearranging the equation, and then we go and compute the inverse Laplace transform to find the time domain solution. All right, so we have an example here. We're given an ODE of x double dot plus 3x dot plus 2x is equal to 0. And we're given some generic initial conditions, x of 0 equals a, and x dot of 0 equals b. And then we're asked to find the solution of this. And of course, we're going to use the Laplace transform method. And in fact, I'm going to have you guys work on this. And then I will either come back up here and solve it today, or I'll solve it on Monday next week.